course, what chemists like to call is that these, the lower ones, which correspond to these bonding orbitals, few electron orbitals that from the beginning. This leads to the so-called valence band because you're filling this up. This is all the valence electron. And up here in the jargon of chemists, these are virtual orbitals. They are not physical orbitals. They are just the byproduct, if you like to think of it that way, byproduct of your calculation. Because if you change your calculation, change your basis, these virtual orbitals, so-called virtual orbitals, may change because they don't have a meaning because you have not filled them yet. Once you fill them, then they have meaning because they would have processed. You can then describe that electron with a particular energy. So these so-called virtual orbitals evolve into so-called conduction band, and they are unfilled, essentially unfilled electron energy level. So this is the origin of these physics picture, right? This physics picture, density of states, and energy level like this. Okay. So the concept, I hope that you appreciate this idea of density state. Density state, in some sense, is light degeneracy. It just arises because of the periodicity, because the sheer number of combinations you may have in a particular direction. I'm plotting here in a very linear way that you think of it as one-dimensional, linear chain type molecule that you combine. So of course, this linear chain molecule have a periodicity, and you can extrapolate this linear chain from with a certain periodicity, let's say the x direction, and then to the y direction with a different periodicity, and you can see the direction with control, the nature of these band structure that you see. Okay, so that's that's the basic principle that you have with these band structure and band gap. And the band gap simply is just when you evolve into like that, simply into correspond to the energy difference between the top of your valence band to the bottom of the conduction band. So it's really, in chemist jargon, it's HOMO to LUMO transition. I mean, this is what frontier orbitals. So these are the frontier orbitals because they are at the top, and the frontier orbital in chemistry is the one that controls the chemistry because this is the one that the electron transfer will occur and therefore change the compound. Right. So this is and in solid state material, this is the same way because this corresponds to a transfer of electrons from one transition to another from this valence band to conduction band, and something interesting will occur when you get excited that way. So last day we were talking about this, and we were thinking about. I want to just in passing mention a couple of things that's kind of interesting. Is that this optical property of these materials, this metal insulator and semiconductor, they are all related to solid state physics, of course, that you can find in any solid state physics book that you got. So the interaction here we are talking about optical interaction. So you're talking about light interactions, and we have this solid interacting with visible or ultraviolet light or even UV light, and what will happen is that the appearance of your solid, the color that you see with your metal and so forth, correspond to, of course, the absorption and reflectance in the visible region of the electromagnetic spectrum, typically 1 to 3 electron volts. And so if you have solid with an energy band gap in this range, you would appear as color, So you would have color. You would go from depending on how you absorb this visible spectrum, you generate color in that range. If the band gap is below 1.5 electron volt, basically lower than the visible spectrum, you go into the infrared region, then the solid will appear dark shiny, which is what most metal that you see, right? Most metal you see are dark and shiny object, and that's due to the lack, effectively the lack of a band gap, that you don't really have a band gap. And if you look at silicon, silicon has an indirect band gap of 1.1, right? If you look at silicon wafer, it's totally shiny and dark as well, and that's the reason. Even for semiconductor, if your band gap is below this 1.5, electron will absorb in the infrared, so you would not see any. You see a dark object in your material. But if you have a material that's above 3 electron volt, basically in the ultraviolet regime, right? For example, all these transparent conductive oxide materials, so-called indium tin oxide or ITO, or zinc oxide or titanium oxide, things like that. Those materials will be transparent. The reason why they are transparent is because their band gap is about 3 electron volts. So zinc oxide, for example, has a band gap of 3.37 electron volts, and tin oxide is another transparent conductive oxide. It has a band gap of about 3.7 electron volts, even higher than zinc oxide. Okay, so all these material appears as transparent. It's just like glass because the band gap is high, and so they just go right through. Okay, and sometimes titanium oxide is also one of these TCO material, but if you make it small, nano powder form, you will see the TCO property. But if you have micro powder, right, they depend on size, then optical scattering takes place. And if you have any kind of scattering occur, you will see white, you turn it into white light. So the scattering causes this white appearance. This is also the reason why you have fog, right? In fog, in the atmosphere, in early morning, for example, fog is kind of white cloud region, and that's because of water droplets in the micron size range. Then you're scattering and you see fog. That's the same phenomena that why you got white paint that you got. If you sprinkle piece powder in there of the right size, then you get scattering, and you get this white. Even though inherently, if you make a crystal of TiO2 or big crystal, or go into a very, very small nano powder regime, nanoscale regime, you would get transparency through this. Okay, so that's the idea of this. So even though, the word of caution is that even though you look at powder, they may appear white, you have to be careful, because that may not be the inherent color, so-called inherent color of that material, because they could just due to scattering of this crystal plane rather than in the inherent band gap of that material itself. Okay. So here we have, in the case of insulator and semiconductor, then you will have a band gap, right? In the case of metal, you don't have a band gap because the electron field in one band, and so in this case, insulator and semiconductor, you have a band gap, and when you scan the wavelength, right? If you do absorption spectroscopy, like ultraviolet absorption spectroscopy, the onset of these absorption, right? You measure the absorption of the light, right? But in any UV spectrometer that you lay your hands on, then you basically, whatever that energy onset, you see absorption onset, that could correspond to the band gap itself, because that is the minimum energy required to make the transition from the valence band to the band. Okay, so in the case of metal, there's no band gap, so the range of excitation can go to 0, and that's sometimes that's the reason you don't see these things. So here we have band gap. So again, so this is an illustration of what I talk about. That you have insulator and semiconductor. You got this band gap, and I'm plotting N here. N, you remember, is the denser state, as I mentioned at the beginning of the lecture. That you have a electronic state and unfilled electronic state. And excitation, absorption of light cause the electron to move across to the unfilled state. So you have these weak spectra. So here you have, for example, if you have a filled state, empty state like this, you absorb light, and this make a vertical transition with the right energy, right? Because you absorb the entire photon. It's a photon absorption is a Western process. So you either you absorb the photon or you don't absorb the photon. And to absorb the photon, you have to have the right energy difference.